Not only was there a real Tower of Babel in the past, the tower and the city that bore its name is being rebuilt today by the world's most dangerous dictator.
We are building it bigger. We are widening the corridors and adding more lanes. We are building a religion, a limited edition. We are now accepting callers.
I believe the tower was intended as a communication device, but not with any so-called ancient astronauts, rather with the spirit world of demons and fallen angels.
Come, we'll go down and garble their speech so they won't understand each other. Then God scattered them from there all over the world, and they had to quit building the city. That's how it came to be called Babel.
The biblical story of Babel is completely consistent with all of the evidence. Anyone who denies this fact is simply engaging in fantasy or speculation.
Now, why do words for some things sound the same in many languages, while others with the same meaning are unrecognisable? And why do some verbs, to the frustration of language learners, remain stubbornly irregular? The key to both these questions is how often words are used. I spoke to Mark Pagel from Reading University in the UK. His team have looked at why words such as those for the number 2 are similar in different languages, whereas other words diverge.
We started with the observation that some words in the Indo-European languages evolve very rapidly and other words evolve very slowly. For example, take the English word for the thing that we call a bird. The Italians call it uccello, the French call it oiseau, the Spanish call it pájaro, the Greeks say puli, and the Germans say Vogel. But then you take the meaning two objects. English-speaking people say two, the French say deux, the Spanish say duo, the Italians say due. All Indo-European speakers use a related sound for that meaning of two, whereas we use very different sounds for the meaning bird. We wanted to understand why that was the case.
And how did you go about doing that then?
So as evolutionary biologists, we began with a sort of genetic perspective, and we realized that some genes evolve very rapidly and other genes evolve very slowly. And one of the things that happens in genetic evolution is that the rate at which a gene is expressed in your body, how often it's used, can be related to how rapidly it evolves. And so we sought an analog to that in language, and what we came up with was the idea that in language, different words are expressed at different frequencies in normal speech. What we discovered was that the words that are used very frequently in everyday speech are highly conserved across the Indo-European languages, and the words that are used infrequently in common speech are free to evolve at a high rate. And so you take words for the numbers, like 2, the example I gave, it's used very, very frequently in speech, and it evolves very slowly. And you take a word like dirty or bird or some other words, they're used very infrequently and tend to evolve at a high rate.
Now, you've come at this from as you were saying earlier, you're an evolutionary biologist. Are you surprised by the degree of correlation between how language seems to evolve and how genes evolve in biology?
Well, we're not so much surprised with the correlation between genetics and linguistics. I think what we're more surprised by is that a single factor, the rate at which or the frequency with which a word is used in common everyday speech, can predict so much of the variability across the Indo-European languages in how rapidly a word evolves. And so the single factor, the frequency with which we use words, can explain about 50% of the variability across languages. Before our work, no general linguistic mechanism had ever been advanced to explain this.
While some words stay similar in different languages through time, other linguistic rules mean that some words converge, as Erez Lieberman and his colleagues at Harvard University have found. They pored over grammar textbooks from Old and Middle English and have come up with a rule for how pesky irregular verbs become regularized over time. I asked Erez about this linguistic evolution.
Our paper is about the life and the death of rules, basically how rules in a language emerge and how they die. In general, the way that a rule in a language forms is that you have some new emerging rule, and then there's tons and tons of exceptions to it. And what we showed is that for the case of the ED rule, which we use to form the past tense, today I help, yesterday I helped, the exceptions actually died over time. And the half-life of an exception, so its sort of expected lifetime, is proportional to the square root of the frequency with which it's used. So if an exception is used 100 times less often, it will regularize 10 times as fast.
Which would explain why the very well-used verbs like to have and to be have stayed irregular over all of this time.
Exactly. What's happening is that we're really preferentially losing the really low-frequency verbs. But the high-frequency verbs disappear so slowly that verbs like be and have will probably be around in their irregular form for the lifetime of the language. Really common exceptions are very, very stable.
Now, your team are from the Programme for Evolutionary Dynamics. How alike are linguistic and biological evolution?
That's a very big question. Biological evolution, we've just got tons of data. You can get the complete genome of any species, and that gives you at least a rough approximation of what the evolutionary information is within that species. There is not a good equivalent for a language. So one very big difference between studying biological and linguistic evolution is in the context of biological evolution, you've got tons of data. In the context of language evolution, you don't, and it's so bad that, you might spend years of your life in Widener Library reading Middle and Old English grammar textbooks just to get a data set suitable. That said, it's well known that in the case of biological evolution, very simple mathematical models will be extremely explanatory in terms of describing the changes of an organism, and in particular the genome of an organism over time. The jury is still out in the case of language evolution. Our paper is one of very few examples of a simple mathematical principle really capturing the change in a language over time